So hopefully now that we have a sense of what our galvanic cells look like and how to balance the reactions that go along with them, the red and the ox, we're going to look at cell potentials. And the potential word there is about energy. The cell potential is a measure of how much energy can be carried through the cell. As the electrons flow from left to right in the galvanic process, how much work can we make those electrons do? You guys know from experience that a fully charged battery does more work per unit time than a run-down battery, right? So as the battery runs down, its cell potential decreases to the point eventually where it can't operate the piece of equipment that it's attached to. So it's a measure of the ability for electrons to flow through a circuit. And it's not about the wires of the circuit, it's about the source of electrons and the destination for the electrons. How can they flow through the circuit? And the unit that we use for cell potentials is the volt. Capital V as our symbol. And a volt is a derived metric unit. It's not one of the standard SI or metric units that we talked about in Chapter 1 last semester. It's one that's derived from others. 1 volt is 1 joule per coulomb of charge. That's a capital C for coulomb of charge. So J equals the same joule energy unit we've had before. And C is coulomb. That's the SI unit for an amount of charge. So this is a metric derived unit. Okay, it's important to always remember that voltage has energy in it. Energy is part of it. How many joules per coulomb of charge? A coulomb of charge is a charge on a mole of electrons. So if you think about it, there's kind of a kilojoule per mole unit in here like all of our other units for energy that we've had in the past. So we'll put that up here. 1 mole of electrons is 96,500 coulombs of charge. So the coulomb is related to moles of charge. This number right here is going to change by every textbook and author and instructor that you come across, based on how many sig figs they want you to carry. For us, 96,500 is fine. When you're out and get a job in the real world, maybe you're an engineer and they want you to use 4, 5, 6, 7 sig figs on that. Just do what the boss says. But for us, for now, a coulomb of charge, we're going to call it a mole of electrons, 96,500 coulombs of charge. And coulomb, again, is just a measure for a total aggregate amount of charge. So if we add up all the charge on all the electrons in 1 mole of electrons, we'd have that much charge to be transferred. And at standard state, okay, getting ready to do some calculating here. So at standard state, the conditions are 1 molar concentration for each ion involved, 1 atmosphere for each gas, so 1 atmosphere of partial pressure for each gas, not a total of 1 atmosphere for the cell. Each individual gas has to have a 1 atmosphere partial pressure, and 25 degrees C or 298 K. So that's a little bit different than standard gas conditions, or standard for electric, it's not 0 degrees, it's 25 degrees C. This is usually implied in all your problems that we're going to come across for this class. If it doesn't give you a temperature, the default is 25 degrees C or 298 K when temperature matters in your calculating. Okay? So when we operate either an entire cell or a half cell at these conditions. So at standard conditions or at standard state, the energy of the cell, we refer to that as E0. And that has our units of volts that we talked about. Okay, so E0 for either a cell or the reduction half or the oxidation part. So you're going to see E0. E0 always means at these conditions. The zero part does. You'll see this as E cell. E0 for reduction, RED. E0 for oxidation. So cell means the whole thing. Red and ox mean the individual parts. Each one has a standard potential. Okay. And we're going to see how, if we know the standard potential of red and ox, we can calculate E0 for the entire cell. Okay. So these values that we're going to use at standard conditions are tabulated. In your textbook, back in the appendices, table C9 on appendix page 38, A-38, has a reduction potential table. So if I'm in page A38 here, and it's a 2-page long table. When I assign you homework problems and things like that, I'm going to give you the potentials because I know some folks don't have as good of access to their textbook as others. But it's a big, gnarly table there with a whole bunch of different reactions. And just like in the thermodynamics table, it's important that you know what you're looking for because you'll find the same element sometimes more than one spot on the table. For example, iron has 3+, 2+, and 0 as its oxidation possibilities. So in the table, you might find a 2-electron reduction of iron and a 3-electron reduction of iron, and a 1-electron reduction of iron 3 to iron 2. So make sure you know what's being oxidized, what's being reduced, and how many electrons when you look at the table to find the potential, the standard potential. So the way these are laid out is with the positive potentials, they're laid out in potential order. Positive up here at the top, and up at the top, positive potentials for reduction. This is a reduction potential table. That's also important to keep in mind. When you're looking at your balanced redox processes, you're going to have one half cell that's oxidation, one that's reduction. You're going to look them all up as reductions, even if it's oxidation in your problem. So you look up the reduction potential. Okay, so in the table like this, it can be kind of a bummer because you have to hunt and peck and find the ones you're looking for because they're listed in potential order, not in an element order. So at the start, up here at the top, the positive, highly positive reduction potentials, plus 2.87 volts is where fluorine reduces. Now, 2.87 volts doesn't sound like a lot because we're used to 110 volts and 220 volts in our standard household type appliances and outlets, but that's a lot of potential in electrochemistry terms. Okay, that's a very positive potential. And as you go down here, get to the bottom of the second table, down there at the bottom, lithium reducing from Li plus to Li as a solid reduces at minus 3.05 volts, which again doesn't sound like a huge potential, but in electrochemistry terms, that is a very negative potential. Okay, we're dealing with all of our stuff within a 6-volt window, right? +3 to -3 ballpark is where most of our stuff happens. Okay, so you would have to find your element in the table, look it up, look up its reduction potential. Okay, E0 for reduction. Okay. If we wanted to find the oxidation potential, E0 for ox, we'd be flipping the equation because these are all reduction equations, right? Flip the equation, you flip the sign on the E0 that's in the reduction potential table. We're not going to do much of that. Okay, there's a couple ways that we're going to solve the problems we're going to be looking at, and the way that we are going to solve our problems, we don't do any sign flipping from the table values. We're going to do an equation that does the sign flipping for us. Just like in our delta H, delta S, delta G problems, we didn't do any sign flipping the equation we used did the sign flipping for us. All right, so we look up those cell potentials. So when we write out our half reactions, when we go through the half reaction method for solving a problem, we have our reduction half reaction, our oxidation half reaction. We end up balancing those just like we did. We had 3 examples of those. We will look up in the table when we want to know our cell potential at the end. We'll balance the equation and calculate E0 for the cell. And we do that from the reduction potential from each of the participants. Okay, so what got oxidized, what got reduced, look up their reduction potentials, and we're going to plug them into a pretty straightforward formula to calculate E0 for the cell. Okay? So that's what we're about ready to do. I don't want to run my video too long or I can't load it on YouTube. So we're going to work our example in the next video. But we're going to look up some E0 values in the table, balance a half reaction or two, and I'm just going to choose one we've already balanced so we know what it looks like. But we're going to calculate E0 for that cell. Okay? So click on the next video and here we go.